So we have this region bounded by these graphs right here, and we want to revolve it about the line, the horizontal line y equal to 1, and then find the volume of the solid of revolution. So this is what the graph looks like. This is the line, this is the graph y equal to the square root of x plus 3. This is the line y equal to 2, and this is the line x equal to 0, and this is the line x equal to 5. And this is the axis of revolution, the line y equal to 1. So what we want to do is take this shaded region, bounded region, and revolve it around this line, and then find the volume of the solid And when we revolve that bounded region around about the line y equal to 1, this is what the solid revolution looks like. And so because this is the axis of revolution, we end up with a hole in the middle. And this is what a typical disk looks like. And so this disk, which corresponds to this rectangle, has a hole in the middle. And so what we want to do is to get the volume, without the hole. And so we're going to find the volume of the entire solid, and then find the volume of the hole, and then subtract the volume of the hole from the volume of the entire solid. Now, for the volume of the entire solid, the radius is going to be from the axis of revolution to the graph y equal to the square root of x plus 3. The hole will have the radius from the axis of revolution to the line y equal to 2. And so the outer radius, which is the distance from the axis of revolution to the graph y equal to the square root of x plus 3. And so we have the square root of x plus 3, which is from this graph, and the axis of revolution is the line y equal to 1. And so to get the distance from here to here, we'll do the square root of x plus 3 minus 1, which is the line y equal to 1. So this is from the curve, and the 1 is from the axis of revolution, which is the line y equal to 1. And so we'll get the square root of x plus 2. And that's going to be for the outer radius. Now for the radius of the hole, it'd be from here to here. But this line is the line y equal to 2, and this line is the axis of revolution, which is y equal to 1. So we have 2 minus 1, which is 1. And so for the outer radius, we'll call it big R of x, and for the inner radius, we'll call it small r of x. And so again, the volume of the solid that we want is going to be the volume of the entire solid minus the volume of this hole. And so for to get the volume of the entire solid, it'd be pi times the radius square, which is the big R, and then dx. And then notice that x ranges from 0 to 5. 0 to 5. So that's why for our integral limits, we have 0 to 5. And then the volume of the whole, which is the small r of x squared. The whole is also has x ranges from 0 to 5. And so our limits of integration will also be from 0 to 5. And then for the outer radius, it was the square root of x plus 2. And then the inner radius, or the radius of the whole, which is 1. Now, the square root of x plus 2 squared is just the square root of x plus 2 times the square root of x plus 2. And we'll get x plus 4 times the square root of x plus 4. And so that's what we end up with here. And then 1 squared is just 1. The the antiderivative for x is just x squared divided by 2. Now the square root of x is the same as x to the 1/2, and antiderivative of x to the 1/2, we just add 1 to the 1/2, which is 3/2. And then dividing by 3/2. So we end up with x to the 3/2 dividing by 3/2. Antiderivative of the constant 4 is just 4x. 1 squared is 1, and then antiderivative of constant 1 is just x. And then we have the pi right here. And then now we'll evaluate from 0 to 5. So we put 5 here, we get 25/2. And then 4 dividing by 3/2 is the same as 4 times 2/3, which is 8/3. And then if we put 5 here, we get 5 to the 3/2. If we have 5 here, we get 20. And then if we plugged in 0, we get 0, 0, 0. And then here, if we put 5 here, we get 5 pi. So the volume of the solid that we want, all of this minus 5 pi, which is approximately 180.05799. So one more time, the reason we use the washer method is because we have a hole in the middle.